Alright, so we went over our trig identities. And the reason that we need to have those memorized is because we're going to be using them in a couple different ways. But we do need to have them memorized for our test. So today we're going to look at some simplifying using those trig identities. Later on in the next section, we'll also be proving some of our identities, and we also need to know how to use them as well. Alright, so our first example says, use the value that secant of u equals -3/2, and that tangent of u is positive or greater than 0. So find the values of all 6 trig functions. Now, we looked at examples like this in our last unit. However, that was where we used like our unit circle and made triangles with them, found the missing side, and then just used all of our trig ratios to find all of our trig functions. Okay, there's another way that we can do it as well, and that's going to be using our trig identities. So, if on a test or a quiz I say find them using our trig identities, we need to be able to use our trig identities and not the like triangle stuff we did last chapter. Now, if it just says find the trig function, you can use either way. But if I say use your trig identities, we need to make sure that we're using our trig identities. So, the first trig function that they give us is secant. And they tell us that secant of u, that's our variable this time, is -3/2. And then we want to use our different trig identities to help us find our other 5 trig functions. So, looking at our identities, what one might be pretty straightforward and easy to use if we know that secant is -3/2. Yes, ma'am. Yeah, so we could use our reciprocal identity. We don't want to use the 1 over cosine because that equals secant, and I already know secant. You want to use the other one that says cosine is 1 over secant, because then that allows us to plug in what we already know and now find cosine. Does that make sense? Okay, so I'm going to plug in what they tell us that secant is. So I have 1 divided by -3/2. So remember that we need to multiply by the reciprocal of our denominator. So what do we end up with? What's the reciprocal of -3/2? -2/3. And so that's what cosine is. So 1 down, 4 more to go. And here's where it gets not tricky, but just different. There's not like a right or a wrong way to use your identities. It's just whichever way makes the most sense to you. And then there's not like a right or a wrong order to find them in. It's just whatever order, like I said, kind of makes sense for you to use your identities. Does that make sense? Now, your reciprocal identity is always the easiest one to use, so if you can use that one, I would use it. Otherwise, the rest of them are kind of about the same. So, if I have cosine, are there any of my identities that have cosine and just one other function in them? To where if I plug in cosine, I could solve for the other function. So if I use my quotient identity, right, that has tangent, cosine, and sine. So in order to be able to solve for one of the other ones, I would have to know 2 of them. Does that make sense? So I know cosine right now, but sine and tangent would still be unknowns, so I would have to know one of them. We're on the right track though. So what's another one that has cosine in it? That's not super helpful because we already have cosine. So we want to find one with another trig identity. Not quite, because that would be the same problem with using our tangent one, that I would have 2 missing. What's the one that I said is really important because it comes up a lot? What's our main Pythagorean identity? Sine squared plus cosine squared equals 1. Yes? So I have a cosine squared, but I can still find that squared very easily. And then we only have sine, right? So if we plug in cosine, then we can solve for sine. Does that make sense? So I'm going to start out by just writing out the identity. Now you don't have to do that every time, but I would suggest while you're learning them, especially, the more you write them out, the better that you're going to memorize them. So it might be helpful, at least while you're practicing them, to go ahead and write them out before you use them. So like I said, we don't know what sine is, so we're just going to leave that as our unknown. But we found what cosine is. Now, just a little, off to the side, just so you know, cosine squared of x is the same thing as cosine of x squared. Okay, so I'm not squaring my x, I'm squaring the whole thing. So instead of having to write parentheses every single time, that's why we put the squared next to the cosine and not by the x. So it's kind of like shorthand. So technically what we can do here is, because we know what cosine is, it's -2/3, we can plug that in and then square it. Because it's cosine and then squared. So what is -2/3 squared? Not quite, because remember I'm squaring it, so I'm multiplying it by itself. So we can square our top and our bottom separately. That's fine. So 2 squared gives us 4. 3 squared gives us 9. And then because it's a negative times a negative, it's going to be positive. Y'all with me? And then it's going to be just like if sine was a variable, right? Like instead of solving for x, I'm solving for sine of u. Does that make sense? Yeah. So in order to move our 4/9 over, what do we need to do? Subtract it. So we have 1 minus 4/9. Well, what is 1 minus 4/9? 5/9. And then again, I'm looking for sine of u. So how would I get sine of u by itself now? That would be if we were trying to get rid of the sine. I don't want to get rid of the sine. I need to get rid of the squared, so we would square root it. But what do we need to be careful about? So when we square root things in an equation, what do we have to add? Plus and minus. And now remember, just like when we square something, when we square root it, we can do it to the top and the bottom separately. So we get the square root of 5/3. But now, when we're looking at a problem, we're not going to have 2 answers. We have 2 possible answers, but now we need to choose which one of those it is. And that's where that additional information comes in handy. So notice that they told us, or we know that secant is negative, right? But they also told us that tangent is positive. And that's going to help us because that's going to help us narrow down what quadrant we're in. So remember, we have so if secant is negative, remember that also means that my cosine is going to be negative. So that's what's over here. So which two quadrants is cosine negative? Yeah. Well, working so far? And then they give you that second piece of information, that tangent is negative, because which two quadrants are tangent negative? Sorry, positive. Greater than good. Which two quadrants are tangent positive? Yeah. Our first and our third quadrant. So then in which quadrant do both of those things happen?
Third quadrant.
Our third quadrant. So we know that that's the quadrant that we're in. So we have to kind of see how we got that. And that's why they give us that like tangent is a positive thing. It's not just like extra stuff. We have to use it in order for us to know that we need to use which one? Positive or negative sign? Yeah, so in our third quadrant, sign is negative. So we would want to choose the negative square root of 5 over 3. Yes? You okay with that? Alright. So then once we have sine, what would another function that would be easy to find from sine? Using one of our identities. Cosecant, right? Because cosecant is going to be the reciprocal of this one. So we would have cosecant of u going to be negative 3 divided by the square root of 5. So then we would just want to rationalize. So we would multiply our top and our bottom by the square root of 5. So we get negative 3 times the square root of 5 over 5. So what are our last two functions that we need to find?
Tangent and I think we do the other one.
Yes. Tangent and cotangent. So once we find one of those, right, it's going to be really easy to find the other one. Okay, so what was the identity that we wanted to use at the beginning? Yeah, the quotient one, because now we know both sine and cosine, so we can use that identity to find our tangent. So tangent of u is equal to sine of u divided by cosine of u. So I'm just going to plug in. We found that sine is negative square root of 5 over 3, and cosine was negative 2/3. Okay, so we have a negative divided by a negative, which is going to give us a positive, which is what we should get because our directions tell us that it's going to be positive. Yes? Reciprocal identity. So here I need to multiply by the reciprocal of the denominator. So this becomes square root of 5 over 3 times 3 halves. So what happens to our 3's? Nah. I mean, yes, but we don't like the word cancel. What do? They reduce. Yes. Okay, but so we end up with the square root of 5 over 2. And in a similar fashion to how we found some of our other ones, now that we know what tangent is, we can find cotangent. Because it's going to have to be the reciprocal, so 2 over the square root of 5 of tangent. And then just like we did with cosecant, we would just need to rationalize that. So we get 2 square roots of 5 over 5. So let's just make sure. So we found secant because that's what they gave us. So that was our first one. We have cosine is our second one. Sine is our third. Cosecant is our fourth. Tangent is our fifth. And then cotangent is our sixth. So we found all 6 trig functions. Now, notice once we found what secant is, right, we have a trig identity, a Pythagorean identity that has tangent squared and secant squared. So we could have used that to find tangent instead. There's going to be more than one right way to find your trig function. It's just whichever one you think is the easiest for you to use, or just whichever one you kind of notice first, if that makes sense. So as long as you're using your identities correctly, there's more than one way to get to all of your functions. Questions about any of that? So that's one area that we use our identities, is when we're trying to find other trig functions given a specific trig function. The other thing that we can use our identities for is when we have a trig expression, or basically stuff that has trig functions in it, and we need to try and simplify it. So like in this case, notice that we have multiplication, subtraction, and we have 2 different trig functions. So there's a lot going on there. So our goal is to try and simplify it. So either make it into one trig function, or maybe get rid of the subtraction. We want to try and make it look a little bit nicer, because then we could use that, and it's easier to use if it's nicer to use. Does that make sense? And that's where our trig functions, or trig identities, come into play. They allow us to substitute or rewrite things to where they look a little bit nicer. Okay? So that's our goal here, is to simplify. So what do we want to do first? Ideas?
You need to transform cosine squared x into cosine x squared.
I mean, those 2 things are the same thing. They are equivalent, but it's not going to help us simplify stuff. So what do we notice about our expression? I have a cosine squared, but what else do we have?
You get 2 signs.
I have 2 signs, okay? Which is going to be helpful, but be careful, because a lot of people see the subtraction and just want to go sine minus sine is 0, right? But if we think back to like, okay, if this was an x and a y, right, could we subtract my x's here? No, because my cosine squared, or like my y squared, is attached to it with multiplication. We can't just like start crossing stuff out. Are you all with me? But what could we do instead if we wanted to try and simplify it and maybe like move our x's away?
Can you like multiply the signs together? So you get sine squared.
We can't multiply by anything, because it would be like if I had 4, I can't just multiply by 2 and say those 2 things are equal, right? We want to be able to put an equal sign, so that means that we can't change the value of it. Does that make sense? But is there anything else that we could do? have a technique that we've talked about when I have two things that are the same that allows us to move it away or in front of the other stuff. Yes. Which is called what? Someone help her out. What's it called when we take something out and put the other stuff in parentheses? The opposite of distributing. We are factoring out the x in that case, yes? So like if we factored out the x, we would be left with y squared minus 1. Yes? Here, well, okay. It's been a little bit, so we'll get there. Yes. Now, and this helps us because now the x is just one of the x's instead of having two of the x's. So we want to do the same thing with what we have here. So notice, like here I wrote x's, so that's going to be sine instead. So I'm going to factor my sine out to the front. So what would we be left with on the inside of my parentheses?
Cosine squared x minus 1.
Okay. Now, remember, the whole point of this is to be able to use our trig identities, right? Our trig identities are what's going to help us be able to simplify. So from here, okay, if we look at the inside of our parentheses, okay, that is not one of our identities, but does it look similar to or close to one of our identities?
Yes.
Yeah, because there's a 1 and a cosine squared, so it looks kind of close to which one? The Pythagorean one. Yeah, so let's go ahead and write that out. So I have sine squared of x plus cosine squared of x equals 1. Yes? Now, notice that I have a minus 1 and a cosine together. Yes? So my Pythagorean identity is an equation, which means that I can manipulate this and move things from the left side to the right side, or the right side to the left side, as long as I do it to both sides. Are we with me? So we can subtract this 1 to move it with our cosine, as long as we do it to both sides. So that would give us 0 on the right side. But notice that inside of our parentheses, we don't have a sign with it. So what could we do with our sign? Stuff. Okay. Yeah, we can subtract our sign from the left side. But then we would also have to subtract it from the right side. So we get cosine squared minus 1 equals negative sine squared of x. Are we all okay with how I got that? Yeah? Okay. Now, notice if I have equal signs, just like if I have A equals B, right? Anywhere that I have an A, I'm allowed to substitute a B for that into my equation. The same thing is true here. I have a cosine squared x minus 1 equals negative sine squared of x. So we're allowed to substitute whatever it equals into our equation. So instead of writing cosine squared x minus 1, I'm going to write negative sine squared of x. And now it's just like normal multiplication, right? If I have an x times an x squared, right, I end up with x to the third. So if I have a sine times a sine squared, we end up with sine to the third, but because our second one is negative, it will be negative sine to the third. And that's much simpler than what we started with, right? Now we only have one trig function instead of two, and we got rid of both the multiplication and the subtraction. Does that kind of make sense? Ready to look at another example? Alright. So, this time we have sine t plus cotangent of t times cosine of t. So realize that whenever I'm showing you different types of problems, I am not going to be able to show you every single type of problem that you could ever see. Because there's an infinite number of combinations of trig functions and operations that you could potentially see. What I'm trying to give you is different techniques that you might be able to use with other types of problems as well. So the first technique that we talked about was like factoring something out. Could we factor something out of this expression? We can't factor out a t, because remember that t is like inside of my cosine, or inside of my sine. Just like if I had a square root of x, I can't factor the x out, because it's inside of the function. So do we have anything that we have multiple of that we could factor out? No, we don't. So we can't use the same technique that we used the first time. So we need to do something different. Right? So something that I noticed is that I have sines and cosines, and we also have a cotangent. So anytime that we see a tangent or a cotangent, and especially if it's with sines and cosines, that is a good indication that we're going to use our quotient identity. Okay? So our quotient identity tells us that cotangent equals what?
Cosine.
So I'm just going to use that identity and rewrite that instead of cotangent. So from there, notice that we have a fraction and we have multiplication. So how do we multiply a fraction by something else?
Turn that one into a fraction.
Yes, so that's technically over 1. And then what would we do? What do you mean by cross multiply? You multiply straight across. Does that make sense? So we would do cosine times cosine gives us cosine squared, and then sine times 1 is just sine. Yes? Alright, well we're getting closer, because now instead of having 3 trig functions, we only have 2, so that's helpful. However, we still have like addition and a fraction going on there. Okay? So if I wanted to add those two things together, okay, what would we need to do?
Get a common denominator?
Yeah, get a common denominator. So think about like if we had 2 plus 1/3 and I wanted to simplify those, right? This is technically over 1, so we would need to multiply the top and the bottom by 3. In order to simplify. Yes? We want to do a similar thing here. Because notice that my sine is technically over 1. So if we want to combine these, we need to make them have the same denominator.
Should be sine squared g.
Yes, so we need to multiply the top and the bottom by our other denominator, which is sine of t. Because that's what we need them to be the same in order to be able to add them. So then, yes, if we multiply, we would get a sine squared of t on top, and then a sine of t on bottom. And now that my denominator is the same, we're going to add them, but be careful, because it's not 2 sine t on bottom. Just like over here, I didn't end up with like 3 plus 3, which gives me 6 in my denominator. The denominator stays the same, okay? So I'm going to add my numerators. But then the denominator just stays the same. Okay? But then we can simplify that. What is sine squared plus cosine squared? That's 1. Using our Pythagorean identity. So we get 1 divided by sine of t, which, if at all possible, we want to not write things as fractions. So using our reciprocal identity, 1 divided by sine of t is cosecant of t, which is nice. We took something that had 3 different trig functions, 2 different operations, and we just ended up with a single trig function.
I did sine cosecant and cosine secant.
It is a little confusing because like your s's and your c's are switched.
Well, just like if you're cosine, cosecant, these two, they could be together.
Not quite.
Guarantee it's going
So we use a Pythagorean identity for the sine squared. And then the bottom one we use cosecant.
We use the reciprocal identity. Yep. So a couple of things to note on these types of problems. 1, sometimes you can use different identities, like I said on the last one, and still end up with the same answer. So as long as you're using your identities correctly, I'm okay with one person having 1 steps and then another person having different types of steps. Does that make sense? But what's going to be important about that is notice that none of these steps are super complicated, okay? But there are a few steps, and sometimes you will need to go back and correct yourself or try something different. So what's going to be really important is 1, you have to show your work, okay? There is no way to go from my first step to my last step without showing anything in between. If I can't do it that quickly in my head, I'm pretty sure most of y'all can't do it in your head. The other thing about that is even if you show your steps, you need to make sure that they're written out very clearly and very neatly. That way, if you need to go back and fix something, you don't have to erase all of your work. You only have to go back to the part that you need to fix. Does that make sense? Also, notice that really the only trig stuff that we did were my last 2 steps. We're substituting sine squared and cosine squared for 1, and then substituting my reciprocal identity. And I will tell you, for the most part, pre-calc students don't struggle with the being able to substitute for 1 and cosecant. They struggle with the algebra steps. Does that make sense? Like, this isn't new stuff. Finding a common denominator, adding fractions is not new. But I think it can be a little intimidating when you start putting like cosines and sines and stuff instead of just normal numbers. So if it helps, like, refer back to like, okay, what would I do if these were just like fractions with numbers? Okay, how would I add these? Or how would I subtract these? Or how would I simplify these? Do that thought process first, because the process is going to be similar for your other types. Does that make sense? Great. Let's look at one last example. So again, we have addition. If we have addition, right, this says to perform the addition and then simplify. So what do we want to do? Or how do I add 2 things that are fractions?
Find a common denominator.
Find a common denominator. So notice that like here, this would be similar to if I have 2 things that have completely different denominators, right? You would have to multiply each of them by something in order to be able to reduce. The same is going to be true for this one. So notice on my first fraction, it's missing a sign. So we would need to multiply the top and the bottom by signs. On our second one, it's missing a 1 plus cosine. So we would have to multiply the top and the bottom by 1 plus cosine. So then we're going to simplify. So sine times sine is sine squared of theta. And then we have sine of theta times 1 plus cosine of theta. Then we're adding cosine of theta times 1 plus cosine of theta. So now that my denominators are the same, what can we do? Add them. So we get sine squared of theta plus cosine of theta times 1 plus cosine of theta divided by sine of theta times 1 plus cosine of theta. So what do we want to do next?
Simplify your numerator, John.
How so?
Well, you could like distribute property for the numerator, so cosine theta times 1 is cosine, and cosine times cosine is cosine squared.
Yeah, so we want to distribute that cosine. I agree. The thing to be careful about is a lot of people will see the 1 plus cosine and the 1 plus cosine here, and they want to reduce those. But be careful because notice that we have an addition sign here. So that would be like if I had x plus xy, right, divided by y, I can't reduce my y's because it's not multiplication on top, it's addition. Like if we just had just xy, then we could reduce our y's. But anytime we have addition, we can't. So yes, we do want to multiply or distribute our cosine. So we get cosine of theta plus cosine squared of theta. Now, do any of us notice anything about our numerator?
You got sine squared and cosine squared.
I do. Which, notice that all of those are separated by addition, so we can rewrite them in whatever order we want. So we would have sine squared of theta plus cosine squared of theta plus cosine. And now what does sine squared of theta plus cosine squared of theta equal? 1. So now notice because basically 1 plus cosine is like its own factor, right? So even though it's plus or it's addition, I can still reduce it because in my denominator, I'm multiplying that by sign and not adding or subtracting it. Yes, sir?
I kind of got lost between the part where we turned 1 plus cosine of theta into cosine squared theta.
Here, I just distributed. So cosine times 1 is cosine. Cosine times cosine is cosine squared. Does that make sense? And then all I did was change my order. So I switched my cosine and my cosine squared. That way my sine squared and my cosine squared were next to each other. And then using my Pythagorean theorem, I know sine squared plus cosine squared is 1. Okay, you want to do it? So now when we reduce, remember, be careful. This is one of the reasons why I don't like the word cancel. Because the numerator doesn't just go away. It doesn't just disappear. It reduces, so it reduces to 1. So we have 1 divided by sine of theta,
Which is
which is cosecant. Okay. So again, we start with something that has addition and fractions and lots of funky stuff. We end up with something that's just kind of nice, and it's just one function.